Hello students, in continuation with lecture series on electronic devices for semiconductor physics, in the previous lecture we discussed the free electron theory of metals and the classical quantum and the Brillouin zone. Now we are going to discuss Fermi level, Fermi energy and numericals on the same. Please subscribe to the channel before continuing further. Okay. The very important question, define Fermi level, what is its physical significance, and you get a numerical on the formula for Fermi level. Now, as we are aware that the insulators have a large band gap between the conduction and valence band, and semiconductors, the band gap lies midway between them, like round about 0.68 electron volt. The metals are literally, the bands are overlapping here. So Fermi energy is basically a concept in quantum mechanics that is referring to the energy difference between the highest and the lowest occupied single particle states in a quantum system of non-interacting fermions at absolute zero temperature. That means the value of Fermi level at absolute zero temperature, which is minus 273.15 degrees centigrade, is known as Fermi energy. It is also the maximum kinetic energy an electron can attain at 0 Kelvin. And Fermi energy is constant for each solid. The distribution of energy states in a semiconductor is explained by Fermi-Dirac statistics, since it deals with the particles which are having half integral spin like electrons. So the fermions obeying Fermi-Dirac statistics, that is, are obeying the Pauli's exclusion principle. Again, you can see how many times they have asked you what is Fermi-Dirac distribution function, explain the meaning of each term, give the physical significance of Fermi-Dirac distribution. So the Fermi-Dirac distribution function for an electron with energy E is given by Fe is equal to 1 upon 1 plus exponential into e to the power of minus EF upon KT, where EF is a constant known as Fermi energy, K is Boltzmann constant, and T is absolute temperature. So this function gives the probability of finding the electrons in various energy levels at given temperature. You can expect a numerical on this formula also. Now, Fermi-Dirac distribution function can be applied to all particles which are identical, indistinguishable, and they are obeying Pauli's exclusion principle. Such particles are called fermions. Now, what is the effect of temperature on this Fermi function helps us in deciding the Fermi level. See, at absolute zero or 0 Kelvin, you can see the Fermi level. Then when we have increased the temperature, and then at a much higher temperature. Mathematically, probability of occupation at T equal to 0 Kelvin, the energy level is lying below the Fermi level, and all Fermi level are occupied, the energy levels are occupied. It indicates that the energy level below Fermi energy level is fully occupied by electrons and the upper ones are vacant. So this gives rise to 100% probability that the electrons are occupying energy levels below the Fermi level. When E is greater than EF, that is, all levels above EF are completely filled and all levels above sorry, when E is greater than EF, that is the energy is greater, then the case is different and probability of occupation at T equal to 0 Kelvin and energy level equal to Fermi level, then Fermi level becomes equal to 1 upon 1 plus e to the power of 0. Mathematically, e to the power of 0 is equal to 1. So this reduces to 0.5 or 50% probability for the electrons to occupy the Fermi energy. This diagram we can explain. See here, I will tell you. The probability function Fe lies between 0 and 1, and there are three possible probabilities. One, Fermi level equal to 100% probability to occupy the electron energy level by electrons. Second, Fermi level equal to 0, no probability here. Fermi level equal to 0, no probability that electrons are going to occupy, energy levels will be occupied by electrons, hence they will be empty. Fermi level equal to 0.5 or 50% probability of finding the electrons in the energy level. So basically, Fermi level is just helping us to locate or find the probability of finding the electrons. It will be clear to you here in this diagram. It is a graph between Fermi level function and energy E. See, at this place, when Fe is equal to 1, 100% probability of finding electrons. When Fe is equal to 0.5, it is 50% probability, and here nil. Special cases have been asked in your previous year papers. The most common one is when E is equal to EF minus KT. We put this value of E in this expression here. E is equal to EF minus KT. Our expression reduces to Fermi level coming out as 0.73 or 73%. Hence, 73% of energy states will be occupied by the electron. Remaining 20% of energy states below the Fermi level will be vacant because electrons have moved to states above Fermi level. Numerical is asked on this formula a lot. Like, I will show you one very common numerical that has been asked. Find the temperature at which there is 1% probability that a state with an energy of 0.5 electron volt above Fermi level will be occupied. It is a 5-mark numerical. So the Fermi distribution function is Fe is equal to 1 upon 1 plus exponential into E minus EF upon KT. They have said that it is a 1% probability. So Fe equal to 1%. That means 1 upon 100 is 0.01. They have given that E minus EF is 0.5 electron volt. 1 electron volt is equal to 1.6 into 10 to the power of minus 19 joule, and then E minus EF becomes equal to 0.5 into 1.6 into 10 to the power of, we have changed the factors, so this becomes equal to 10 to the power of minus 20 joules. The Boltzmann constant K is 1.38 into 10 to the power of minus 23 joule per Kelvin. We put all these values here in this expression and cross multiplying and solving the expression further, we get the temperature as 1261.6 Kelvin. Similarly, you can see another numerical which has been asked many times. Find the probability with which an energy level of 0.02 electron volt below Fermi level will be occupied at room temperature of 300 Kelvin and 1000 Kelvin. Once again, we will be using the very same formula of Fermi distribution function. We will put the values, as you can see, change all the values into one form of system, that is CGS or MKS, whatever is convenient, and find the answer for Fermi level. So most important here in this lecture is the Fermi-Dirac distribution function formula. Fe is equal to 1 plus 1 upon 1 plus exponential E minus EF divided by KT. Thank you.